So welcome back. We've been discussing principal components analysis. So remember that if we have data that fall in a linear subspace, we can use principal components analysis to find that subspace and see what's happening in this higher dimensional space. So as a quick example, maybe we have 2 dimensions and most of our data fall in a linear subspace that looks like this. What principal components analysis does is it finds a direction in this 2-dimensional subspace, or you can think of it as a subspace in this 2-dimensional space. And that subspace is going to pass through the middle of the scatter plot. So by passing through the middle of it, what I mean is we're going to minimize the sum of squared orthogonal deviations between the points and the projections onto this subspace. So that's what PCA does. Well, some of you have been asking, what if the points don't fall in a linear subspace? What if they fall in some nonlinear subspace? So just as a quick example of this, perhaps the points do something like this. So they fall along some curve in 2 dimensions. So clearly a line is not, I can't put a line through the middle of this, but I could fit some sort of a curve that passes through the center of this in the same way. So it turns out there is a method that's been around since the 1980s called principal curves that solves this very problem. So in fact, if I take us over to the Hasty-Tibshirani Friedman textbook, this was the dissertation of Trevor Hasty, the first author of this book. And if we turn to section 14.5.2, you can see that he offers a description of this method. So let's talk a little bit about this method. As with PCA, I'm going to assume that we start with some n by p matrix, we'll call it X, just as we did with PCA. I'll use a lowercase bold x sub I to indicate the ith row vector, just as we did with PCA. Now our goal is to find some lower dimensional set of scores, or you could call them factors if you want, that I'm going to call y. So y sub 1 through y sub n, each of which is a scalar quantity, is going to be this lower dimensional score. So I want to take these p-dimensional x vectors and find one-dimensional scores. So for right now, we're only going to consider one dimension at a time. We can think of data being generated by the following model. So suppose that f is some function that maps from R1 to RP. And f is also going to be assumed to be continuous. I'm also going to assume that I've got some errors that have mean 0 and constant variance in both directions. So sigma squared is going to be the variance both in the x1 direction, the x2 direction, all the way through the xp direction. So let's just go sketch out a picture to show exactly what I mean by this. So if we had p equal to 2 dimensions, here's x1, x2, and we'll just go give ourselves a curve. So maybe the curve looks something like that. That's a nice curve. So this is f at y equal to some vector. So this is going to be some vector. So f1 at y dot 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 f. Well, I guess in my case I only have 2 of them. f2 at y. All right. So the way to think about this this y is that at some point I have y equal to 0. So that's just like the starting point. Now, as I go, say, in this direction, So let's just move 1 unit. This would be y equal to 1, y equal to 2, y equal to 3. And if I go in the other direction, I have y equal to minus 1 as an example. So y is telling me the position where we're located on this curve. I like to think about an interstate highway. So we could think of this curve as being like an interstate highway. You can think of the y's as being like mile markers. So here is mile marker 0, 1, 2, 3, 4, and so forth. Now, we could also describe our location on this road in terms of latitude and longitude. So if I am here at y equal to 2, so I'm 2 miles from the start of this road, we could also give the latitude and longitude of this point, and that would be something like the x1 and x2 coordinates. So I can either have an equation of the curve and then say where I am through this parameter y, or I can express this in the original coordinates x1, x2 with this vector. Let's go back to our model. Our model is that my observed x's, so this is an x vector. We can think of this as xi1, xi2, is equal to some f at y sub I plus epsilon sub I, where epsilon sub I is a vector. By the way, this whole thing is also a vector. And so what this means is, let's go pick a y. So let's say y is equal to 2. If I evaluate f at y, that puts me at this point in the x1, x2 space. Now then, I'm going to give myself some random error in both the x1 and the x2 direction. So maybe I have a point up here, and so I'm just generating points around this curve by sticking some noise around it. Okay, so this is the set of x's. Each one of these points that I've generated is one of my x sub i's. And so where did that come from? Well, it comes from some point on the curve with some noise. So that's the basic idea of the principal curves model. Well, let's go back to my course packet. I've put together a couple concrete examples for us. What you're going to see is that principal components analysis is a special case of this if we constrain our curve to be a linear function. So this is the notation that we were using in principal components analysis. I have some vector u, and I'm going to take some number of steps y in that direction. So if we come back to this perhaps this is my u vector. And if I take some multiple of u, that's going to give me all points on this line or linear subspace through the x1, x2 plane. So clearly, if I constrain my curve to be a vector, then I get a linear subspace and principal components analysis. Another familiar example is the unit circle with polar coordinates. So let's have a quick review of polar coordinates. So back in high school, you probably would have used theta instead of y. But here's the idea. If this is my x1, x2 plane, and let's take and we'll take the function x equal to the cosine of y and the sine of y, then y tells us the position that we are on this circle. So here y is equal to 0. We could say here y is equal to pi over 2 radians. This is y equal to pi radians, and so forth. And so I can describe any position on this circle by indicating the arc length around it, which is given by this y variable. Alternatively, I could convert that into x1, x2 coordinates by taking the cosine and the sine of y. All right, so that's another example of this. I could generate a parabola as follows. So if I take y comma y squared, this y is indicating the location of that. If we considered some point on this parabola, the point is actually given by y comma y squared. So that would be another way to express this parabola. Alternatively, we could write it in the more usual format where x2 is equal to x1 squared, but we could also express it using this other parameter y, just as we did with the unit circle, or as we did with a vector with PCA. Now let me remind you that with PCA we had some problems with indeterminacy. So what do I mean by that? Well, with this picture, I could have also described this subspace with a different u vector. So this u vector also describes that subspace. Or I could make a longer u vector. So here's yet another u vector that would also describe the subspace. So in general, there were an infinite number of u vectors that all describe this subspace. Unfortunately, with curves, the problem gets even worse. So for example, with the unit circle, I could multiply my parameter y by any constant, and I would have exactly the same circle. So that a could even be negative. So instead of going counterclockwise around the circle, I go clockwise around the circle. In PCA, we resolved this problem to some extent by having a unit length vector. So assuming that our eigenvectors had unit length, well, we could do the same thing here by making sure that the curves are parameterized by arc length. So we still don't know which way we're going to go around the circle with this. We don't know exactly where the starting point is, but at least we constrain ourselves to have differences in y giving the distance along the curve from one point to another. So I'll just point out with the usual parameterization of the unit circle, y gives the arc length around the circle. My parabola example is not parameterized by arc length, and to do so would get kind of messy. Well, how do we estimate the principal curve model? We first need to do roughly the same thing that we did with principal components analysis, which was to figure out how to project an x onto my subspace. So as a quick review, with PCA, we had defined the projection of x onto u, and we worked out a formula for that. And what this thing did was, if I had some u and I had some x, the projection of x onto u was the point on u that was closest to x. So this was equal to x transpose times u, u transpose times u, times u. So this whole thing is equal to the point on u that is closest to x. All right, well, we need exactly the same thing, but for a curve. We're going to call this y sub f at x, which is a vector. So let me draw it, and then what we'll do is come back and look at the formula. So let's say I have some curve. So this is my curve f, and I've got some point out here, which is this vector x. Now, I want to find the point on the curve which is closest to x. And so I'd like to find the point where I have a tangent right here. So here's my tangent line that, that is closest to this. Now, we can think of this as a function of this p-dimensional vector. This thing is going to give me a score y. So let's say y is equal to 0 here. This is going to be the distance that we have to travel along this curve until I get to this point that is closest to x. So yf at x is going to give me the position on the curve, so the score, if you will. So this is going to be the position where I am closest to the f. So with that intuition in mind, let's go look at the formula. I think it's easiest to start here. So this is saying search over all positions on the curve mu to find the closest position on the curve to our given x. Now, unlike principal components analysis, where that projection is unique, in the case of a curve, there could be multiple values that satisfy this. So as an example, let's say I had a parabola. And if I had some x here, so there's my x, on the axis of symmetry, notice there would be two locations on the curve that are closest. So that's a problem because my function is not well defined then. This x would map to two y's on the curve. So what are we going to do about that? The answer is we'll take the position with the larger score and use that one. So that's an arbitrary decision. We could have taken the smaller one and everything would still work out. But for this function to be well defined, you've got to pick one of them. Now that we know how to get from x's to some position on the curve, we can now define the objective function. So the objective function is the same as one of the objective functions we used for principal components analysis, which is usually squares. So we're going to choose f that minimizes the sum of squared orthogonal deviations from the curve now, from the curve f, as opposed to the line. So we used lines with principal components analysis. Now we've got this curve f. So how are we going to find this? Well, the principal curve algorithm iterates between finding a curve f and then projecting the points onto that. So the way we start this is we choose the first principal component as our curve. Then with the scores fixed, we could, for example, fit a smoothing spline. So we would have p different smoothing splines and estimate those as functions of the y's. With the curve fixed, then we reproject the x's onto that and we toggle between that until no change is realized. This algorithm has a close relationship to the power method of computing eigenvalues, and if we constrained our function to be linear, this algorithm would get us to the first principal component. So let's do an example. I'm going to generate some data where I know the answer. Let's go generate a semicircle. So to do that, I am going to take 100 random uniform values between 0 and pi. So if you remember your trigonometry, this is 0 and this is pi in the unit circle. I'm now going to generate a sequence of theta values, I'll call them theta 2's this time, so that I can generate the true f. So this is just a grid of theta values. Well, let's go cook up some data that follow exactly the formula that we've been using. So my data, my observed data, is just going to be the cosine of my random thetas. So that's going to be the x1 position on my curve. And then I'm going to add some random noise to it. The x2 position is going to be the sine of theta plus some random noise. So the way to think of this is I've just generated a bunch of points on the curve. Then I've added some random noise. Now if I plot it, I get all the black points shown on this plot below. This next command is going to superimpose the true f, and I'll do that in red. So we'll just take the cosine of theta 2 and the sine of theta 2, and so we can see this red line is giving us the true semicircle. We're trying to estimate that red curve with our algorithm. So in order to use principal curves, we can download the principal curve library in R. So this was due to Trevor Hasty. And we estimate a principal curve simply by passing this X matrix to it. And we get a fitted object, which is a list. So this fitted object only has a couple components, but unfortunately, the names of these don't match what is in my course packet. So S is going to be an n by p matrix giving the coordinates of the curve. Now, the tag variable gives the order along the curve. So it will sequence our n observations along the curve. So if I were to do a lines command of fit$s, this is going to give me two-dimensional points, and we're going to give it this ordering. So fit$tag, what we get is the black line. And so the black line does a very good job of approximating the red curve, except around the endpoints. So principal curves has some difficulty capturing that last bit of curvature on the ends of the red curve. But once you get a little bit beyond the ends of the curve, the black curve and the red curve fall pretty much on top of each other. Also part of this fitted object is an n-dimensional vector, so an n by 1 vector lambda. Lambda is like my y value. It's the thing that parameterizes the curve. So an alternative way to show the fitted curve would be to simply order by these lambdas, so go from the smallest y to the largest y, and plot the corresponding s values. So either one of those get us to this black curve. Now I've also shown the projections of x onto this black curve. You can do this with the segments command. So segments draws a line segment from each row of dat to each row of fit$s. In my little problem here, I know the true values of theta. You can think of theta as being a latent variable. So how does my estimated values, so that's these fit$lambdas, compare with the true thetas? And the answer is really well. So the correlation is 0.994. Now there's a minus sign because the curve happened to go in the opposite direction. So instead of starting here and parameterizing larger thetas going this direction, the software ended up choosing the origin, if you will, over here someplace and going to the right. So larger values of lambda happen when we go to the right. So the estimated curve is going clockwise, and of course the unit circle, the way we usually write it, goes counterclockwise, but that doesn't matter. They describe the same curve. Another component of the fitted list is fit$dist. That's the least squares objective function value. So the sum of squared errors in both the x1 and x2 direction is 1.08. If you'd like to see where that comes from, let's take dat minus the fitted curves. So let's take the points minus the projections of those points onto the black curve. Now I'm going to square this. So if I take E transpose times E, that's like squaring it. And if I add up the diagonal elements, we get exactly the objective function that the principal curve function reported. So I hope that this example has given you a sense for how to use this principal curve function. I've known about the principal curve function for many years, and have worked pretty hard to find applications of it. And to be honest with you, I haven't found that many applications. But I did find one that was kind of interesting. So let me show that to you now. So whenever we have big data and I observe the behaviors of my customers or sampling units on a variety of dimensions, we have to summarize that time series of behaviors. So we typically count or sum variables over time. So a co-author, Bobby Calder, and I called these behavioral features. So for example, frequency could be the number of times that the subject has done something. So this could be the number of times that I watched a particular television show. It could be the number of times that I ordered from a company. It could be the number of times that I visit a website to read the news. Scope is the number of types of behaviors. So in the case of news reading, scope could be the number of sections that I typically read when I visit the paper. Time could be the amount of time that I spend in various behaviors. Sometimes you have a monetary value. So if this were a retailer, frequency would be the number of orders. Scope would be the number of departments that I order from. And time doesn't make that much sense, but monetary would, where this is how much I spend in each of those categories. You could think of spending time as a type of monetary value in an online engagement context. So then the question is, can I extract a latent variable, which Calder and I called a behavioral pattern, from these behavioral features? So let me give you an example of this. We had data from the National Endowment of the Arts where we knew the number of times that people went to each of these arts activities in a year, ranging from jazz concerts to opera, to ballets, to art fairs and history museums. We were interested in two variables. So the first variable was frequency. So how many times did you do an arts activity in a year? That would be XI1. And scope is going to be the number of different types of arts activities that you engage in that year. So how many of these behavioral counts are greater than 0? So if I only do, say, musical stage plays and dance, then my scope would be 2. My frequency would be the total number of plays and dance events that I went to in that year. I'm going to mean center my x's just as I did with principal components analysis. And if we look on the next page, we can see a scatter plot across this sample from the National Endowment for the Arts. The diameters of these circles are proportional to the number of respondents who have that combination. So we immediately see a giant circle at 0, 0. These would be people who don't go to any arts activities, and therefore their scope is 0 arts activities. Of course, if I only do one arts activity in a year, I can only have scope of 1. But if I do 2 or 3 or some or more arts activities, then my scope could be 1, but it could also be 2, and so forth. So we immediately see what I think is a bit of a problem. This thing has to be lower triangular. So there's absolutely no way that I could only do 2 arts events, but have a scope of, say, 6. It's just impossible. I can't do 6 different types of arts if I've only done 2 arts events. Now, what that means is these first 2 points are predetermined. I have to go through this point and this point, but I don't have to go through the middles of the other points on the diagonal. So this really implies that I need some sort of a curve in order to do this well. By the way, off to the right, I have an image plot where the grayscale is proportional to the number of people. So this place where I have all those 0, 0s is very dark. And you can see I'm trying to trace a path through the middle of this. It's almost like if these were mountains, I'm trying to stay on top of the ridge to get across this mountain range. If we look at the bottom pictures, I've shown the principal curve as well as the principal component. So the principal component, of course, has to be linear, and it wants to pass through these 2 points, but the other points are going to pull it down. Whereas the principal curve can take a slightly different pattern. So what would I lose if I just used a principal component instead of a principal curve? The answer is not much. So you can see the projections onto the curve as well as the line, and they're pretty much falling in the same order. So the magnitudes would be a little different, but the orderings wouldn't be terribly different, except off on the right end. So let's blow up this part of the figure and look at it off to the right. Let's take a look at point A. So what we can see with point A is this is the second highest. So this would be someone who's in bucket 5 of the frequency variable and did all 6 arts activities. What we can see with this is on the principal curve, this is the second highest possible score, just behind point B, which is in the highest category of both. But on the principal component, it gets projected somewhat lower. Let's compare A with C. So C is someone who had the highest possible frequency, but only had a scope of 5. So point C actually gets projected onto the principal component at a higher location than the principal curve. So the ordering flips between A and C, depending on whether we use the principal curve or the principal component. So this would be an example where my conclusions might be a little different if I use the principal curve versus the principal component. But by and large, the correlations between the principal component scores and the principal curve scores is very high, and it's not going to matter that much. So this has been my introduction to principal curves. I'll mention that there are higher dimensional versions of this. So Hastie also proposed a method called principal surfaces. This method was extended by Rob Tibshirani, the second author of this textbook. This method gets used a lot with deep learning with autoencoders. So it turns out that autoencoders also estimate curves or surfaces depending on the dimension of the bottleneck layer. So when you get to your deep learning course, you'll learn more about this topic.